Hello and welcome to Controllerstech. This is the 7th video in the STM32 UART series, and today we will continue using the half-duplex mode. In the previous video we saw how to communicate between two STM32 MCUs in half-duplex mode using a single wire. Today we will extend this functionality to interface a sensor that communicates using a single wire. Yes, I am talking about the famous DS18B20 temperature sensor. This sensor uses the one-wire protocol to communicate with the MCU, and since the UART has the capability to handle the communication using a single wire, we will use UART to interface this sensor. I have made a few videos in the past covering this DS18B20 sensor, where in one of the videos we used the PO with microsecond timing. The other video did cover the sensor with UART protocol, but it was rather how to make it work, instead of how it actually works. Today in this video I will cover everything in depth, so you can understand how it actually works at the sensor level. We will analyze the timings on the logic analyzer, and we will also see how the sensor will be able to read these bytes as a single bit. Here I have the datasheet of the DS18B20 sensor. Let's scroll down to the bit timings. Here you can see the timing for the 0 slot. To write a bit 0, the master needs to pull the line low for around 60 to 120 microseconds. And to write a bit 1, the master needs to pull the line low for around 1 microsecond, and then release it. The pull-up resistor will then pull the line high. The important thing here is that the DS18B20 will only sample 15 microseconds after the master pulled the line low. So to write a 1, we don't exactly need to pull the line for 1 microsecond, we can release it anytime within this 15 microseconds frame. Now if we use the UART peripheral with the baud rate of 115200, each bit takes around 8.68 microseconds time frame. Also we will use the standard 8 data bits, so along with the start bit, we have a total of 9 bits. These 9 bits will take around 78 microseconds. This will be the time taken by 1 data byte with the standard setup of 115200 baud and 8 data bits with no parity. The 78 microseconds is within the limits of the time requirement for the DS18B20 bits. We will understand it better on the logic analyzer. Here is the DS18B20 sensor that I am going to use in today's tutorial. It has 3 wires, the red is for VCC, black is the ground, and the yellow is the data wire. I am not connecting it for now, but I have connected the logic analyzer to the UART pin on the Nucleo board. I have already created a project on the Cube IDE. The UART parameters are configured with the baud rate of 115200, 8 data bits with 1 stop bit, and no parity. The pin PA9 is the UART TX pin, and is the only pin available in the half-duplex mode. I have enabled the UART global interrupt, and also set up the DMA for both, TX and RX. The DMA is used in the normal mode, and the data width is set to byte. The DMA interrupts are enabled automatically when you enable the DMA. That is all the configuration we need. Now we will see the UART byte timings on the logic analyzer. Let's define a variable data, and store the value 0 in it. Now we will send this variable to the UART. Basically we are sending the byte 0, so that we can measure its time frame. Let's build and flash it to the board. Here you can see the data on the logic analyzer. We can see the byte 0, and the total time for which the line is low is 82.5 microseconds. This is the time taken by the 9 bits, which contains 1 start bit and 8 data bits. The start bit is the first low bit, and then we have 8 bits with all zeros. This whole arrangement satisfies the criteria for writing a 0 slot to the sensor. In other words, if the MCU wants to send a 0 bit to the sensor, we will send the byte 0. Now let's check the timing for the byte FF hex. Here you can see the start bit, which pulls the line low for around 13 microseconds, and then we have all the ones. We know that DS18B20 samples the data 15 microseconds after detecting the first transition, and the line is always high in that time frame. So the DS18B20 will read this as a 1. Actually, the start bit time is even smaller when we connect an actual device on the other end. So to send a bit 1 to the sensor, we will send the byte FF hex. We now have an idea about how to write a 0, or a 1 to the sensor. Let's see the reset timing now. To reset the sensor, we need to pull the line low for more than 480 microseconds, and then release it. The problem we have is that the UART with the baud rate of 115200 won't be able to do this. Since the total time taken by a byte is even less than 80 microseconds, we can't generate a reset with this baud rate. So here we will use the baud rate of 9600. The good thing about the whole library is that we can simply change the baud rate during the UART initialization, and it will work. Each bit at the baud rate of 9600 takes around 104 microseconds. We already have the low start bit, and if we send another 4 bits as low, we will have a total low time of 520 microseconds. This satisfies the reset criteria where we need to pull the line low for at least 480 microseconds. We will again test it with the logic analyzer first. Let's change the data to F0 hex. The least significant bit is sent first in the UART, therefore the 0 will be sent first here. Let's build and flash it to the board. There is an error here, and that is because the analyzer is set up with 115200. Let me change it to 9600. Now you can see the byte F0 hex. Here you can see the pulse is low for 525 microseconds. Basically after the start bit, we have 4 zeros, which keeps the line low for this much time. Let me add the one-wire analyzer to this channel. The one-wire protocol can see this as the reset condition, so we are good here. Now let me connect the actual sensor, and we will see how it responds to this reset condition. Here I have connected the sensor to the MCU using the breadboard. The green wire is connected between the signal pin of the sensor and the UART TX pin. The orange wire connects the sensor's VCC pin to the 5 volts of the MCU, and the grey wire connects the ground to the ground. I have connected a 4.7 kilo ohms resistor between the VCC and the ground pin. This will act as the pull-up resistor. The logic analyzer is still connected to the TX pin, so that we can see the sensor's response. Alright, let's check the analyzer again. Here you can see the pulse on the analyzer. The data is now C0 hex, instead of the F0 hex. This is because this time the sensor pulled the line low. The one-wire protocol shows there is a reset condition, and it also detects the presence of the sensor. Actually we sent the byte F0 hex for the reset sequence. Since the least significant bit is sent first, the MCU pulled the line low for around 520 microseconds, and then released it. As soon as the line was released, the sensor pulled it back to low for 127 microseconds. Everything happened as per the instruction given in the sensor's datasheet. One thing to note here is that the byte F0 hex was not transmitted fully. The sensor does not know what we are sending, it just sees that the line was low for more than 480 microseconds, so it must be a reset pulse. And as soon as it realizes this, it will show its presence by pulling the line low for some time. We will now write an initialization sequence for this sensor. We need to change the UART baud rate during the run time, so let's define a separate function to do so. The parameter of this function is the baud rate with which we want to initialize the UART. Here we will copy all the initialization code, and just pass the parameter baud to the baud rate. The DS18B20 start function will be used to initialize the sensor. Here we will send the reset sequence to the sensor, and then detect its presence. So first we need to initialize the UART with the baud rate of 9600. Then transmit the data byte F0 hex. The sensor will pull the line low while this byte is still transmitting, so we will have new data in the UART data register. This data byte could be anything but F0 hex. Basically, if there is a presence pulse, the data register cannot contain the same data that we sent. We will receive 1 byte of data via the UART, and copy it in the data variable. Now the rest of the UART operations will take place at 115200 baud rate, so let's initialize the UART again. Finally, we will check if the received data is the same as the transmitted data. If it is the same, that means no presence pulse was detected, and we will return an error. Otherwise return success. Let's define a presence variable. Inside the while loop, we will call the DS18B20 start and store its value in the presence variable. Let's test this part first. Here I am adding the presence variable to the live expression. Let's run the debugger. You can see the presence value is 1, this means the sensor is detected successfully. We will now proceed with the rest of the code. Now we will write the data to the sensor. The DS18B20 write function takes the data byte to be written as the parameter. I have already shown how to write a bit 0 and bit 1 to the sensor. Basically, to write a single bit, we need to send an entire byte, and this is why I am defining a buffer to hold 8 bytes. Now we will extract a single bit from the data byte. If this bit is a 1, we will store FF hex to that position in the buffer. And if the bit is a 0, we will store 0 in the buffer. This way we will prepare a buffer with 8 bytes for a single data byte. Now we will send the buffer to the UART. Let's test the write function before proceeding forward. Here we have the examples in the datasheet, which covers how to get data from this sensor. Basically, we send the reset pulse, and the sensor responds with the presence pulse. Since I am only connecting a single sensor to this pin, I will issue the skip rom command. After that, the convert T command will be used to convert the temperature. So let's issue the skip rom command first, and issue the convert T command. Let's build and flash the code to the board. We will observe these commands on the logic analyzer. You see this framing error because the analyzer is configured with the baud rate of 9600. Let me change it to 115200. Now you can see each data byte sent by the MCU. The one-wire analyzer can analyze this data. You can clearly see the skip rom command, cc hex. The 44 hex is being recognized as the data byte by the analyzer. So the MCU can write the data properly. We will now proceed with the reading. The DS18B20 read function will read the data bytes sent by the sensor. This here is the sequence for the master to read the bit 0 or bit 1. The master needs to pull the line low for more than 1 microsecond, and then release the line. If the sensor pulls the line low again, the bit is a 0. And if the sensor does not pull the line low, the line will be high because of the pull-up resistor, and this denotes the bit is a 1. Note here that the master is the one pulling the line low initially. We can assume this as the start bit of our data. Basically, we need to send the byte FF hex. This will keep the line low for only the period of the start bit, and the line will be high for the rest of the time. As soon as the line is released after the start bit, the sensor will either pull it low to transmit bit 0, or it will leave it high to transmit bit 1. Since we want to read an entire byte from the sensor, we need to send 8 bytes of the data. Let's define a buffer to store 8 bytes to be sent. The variable value will contain the byte received from the sensor. Now we will store the data to be sent to the sensor. We will send the data byte FF hex each time, so that the line is pulled low only for a period of the start bit. Now we will transmit this data using the DMA. The use of DMA here is very important. The data using the DMA is transferred in the background, so for each byte transferred, we can read the sensor's response to that byte. If we send the data in the blocking mode, all the 8 bytes will be transferred before the control can reach the reading function. So we will only be able to read the sensor's response to the last byte sent, and the first 7 bytes will be lost. Once all the 8 bytes have been read by the DMA, the RX complete callback will be called. Inside the callback we will simply set the variable is received to 1. This will help us identify if all the responses have been received. Once we have received the sensor's response to the data bytes we sent, we will start extracting the bits from the bytes. We sent the byte FF hex, and if the sensor did not pull the line low, the data will be the same. And this means that the bit must be 1. We do not care what data we received, all we care is if it is different from FF hex. If the data is different, that means the sensor must have pulled the line low, and the bit is a 0. We have defined the value with an initial value of 0, so the bit 0 is automatically adjusted. After extracting the bits, we will reset the variable to 0, so that this loop does not run again. Then return the value. These are the only functions we need to interface the sensor with the MCU. Let's see the initialization pattern again. So we send the reset command, and the sensor responds with the presence pulse. Then we issue the skip ROM command, followed by the convert T command. Then send the reset command again, and the sensor will respond with the presence pulse. The master will issue the skip ROM command, followed by the read scratchpad command. Then we will read data bytes from the sensor. We will read 2 bytes of data, so let's define 2 variables. We will read the least significant byte first, and then read the most significant byte. Let's build and test this part first. We will convert it to temperature in a while. Let's add all the variables to the live expression. Here you can see we have the data in the least and most significant bytes. Here in the RX data buffer, we either have the byte FF, or F8. This FF hex represents bit 1, and the F8 hex represents bit 0. Let's see it on the analyzer. Here you can see the entire communication frame. We send the reset sequence first, followed by the skip ROM, and convert T commands. Then send the reset sequence again, followed by the skip ROM, and the read scratchpad. Then the sensor sends the data. The bit 0 is represented by the byte F8 hex, where the sensor pulled the line low for a while after detecting the start bit. The bit 1 is represented by the byte FF hex, where the sensor does not pull the line low, and the line remains high for the entire byte. Now we will convert these data bytes to the temperature value. By default the sensor's resolution is 12-bit, and this is how the data is stored in 2 different bytes. Here letter S represents the sign, and for negative temperatures, this sign bit will be 1. We will combine these 2 bytes, and make a single 12-bit data. Let's define a 16-bit sign variable, where we will store the 12-bit combined data. The temperature variable will contain the actual temperature. To combine the data bytes, shift the most significant byte to the left by 8 places, and then add the least significant byte to it. To get the final temperature, we will divide this value by 16. Since the resolution is 12-bit, each bit represents the temperature of 0.0625. This is why we are dividing by 16 to get the final temperature. Let's add the variables to the live expression, and run the code. You can see the temperature value is now being stored in the temperature variable. Right now the temperature is around 18 degrees Celsius. Here I have a cup of cold water, and I am going to dip the sensor inside it. You can notice the change in the reading. I have fast forward this part, but make sure you give at least 2 seconds delay before taking the reading again. The temperature has dropped to about 1 degree Celsius. Now I am holding the sensor in my fist, and you can see the increase in the reading. Everything is working as expected. The sensor responds to the change in temperature pretty well. The one-wire protocol is working fine too. Note that the DS18B20 sensor also uses the one-wire protocol, but if you notice here, the bit timings are not constant. For example, the bit 0 indication means that the sensor will pull the line low for 50 microseconds, and then pull it high for 26 to 28 microseconds. After this, the sensor immediately sends the next bit by pulling the line low again. Similarly, the bit 1 indication is when the sensor will pull the line low for 50 microseconds, and then pull it high for 70 microseconds. The sensor immediately sends the next bit after this, and hence we have different time periods for bit 0 and bit 1. This is why the one-wire protocol using the UART cannot be used for these sensors. Instead we can use the regular GPIO method to read the timing. My point is, please do not ask me to make videos on DS18B20 or DS18B22 using the one-wire protocol. So I hope you understood how to use the one-wire protocol to interface the DS18B20 temperature sensor. You can use this idea to interface other devices which use the standard one-wire protocol. This is it for the video. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.